let's get started. The material I'm going to cover today is called nested model. Okay, and anybody heard nested model before? Okay, and I'll tell you this. If you know how to do factor analysis, factorial experiment, you can consider nested model. Really, the computation is like factorial analysis. Okay, except one thing. Okay, if I have an A factor, I have a B factor, I'll have AB interactions. Agree? Agree? But now, the AB interactions cannot be standing alone. The AB interactions must belong to A or belong to B. Cannot be, in other words, is that originally we say, maybe we can say A is the father, B is the mother, the AB interactions, the kids, right? The sons or the daughter. But now, we cannot let them just say that, the kids be alone. The kids must assign to the dad or assign to the mom. And why is that? Okay, so far so good? So computationally, we first calculated, and then we said, hey, you stick with A or stick with B. And the second thing I want you to understand, nested, just put it down, okay? This may not be in any official document, but it's my language that I consider easy to visualize. Okay? It's similar but not identical. So in other words, is that the property is similar but not identical. Okay? So put that down first, because sooner or later you're going to face this kind of situations in the real world. The problem is that first you can pretend it's factor analysis, but at the end you have to do something about it. And what's factor similar but not identical? Consider that I have hospital A, hospital B, hospital C. Okay? In each hospital, I have 3 different imaging techniques, MRI, CAT scan, ultrasound. Okay? And so no matter which hospital, you can get those images done if you have, certain diagnostic under certain insurance, right? But those 3 hospitals, those equipments are not exactly the same, but they're very, very similar. So, if you go to Novant Health, they said, give me MRI. You go to Atrium, they say, I will give you MRI. The image, pretty much the same thing. So if you look at the books or, go Wikipedia, you're going to see something, that's about the same. But at the same time, because of, could be one from Siemens, one from GM, so the property or the design is a little bit different. So sometimes, maybe for certain cancer or certain hairline fracture is a lot easier to be detected by one type of company and not the other one. So now we know that there are hospital and there are equipment interactions, right? So I say I have 3 hospitals, 3 equipment. So I'll have hospital equipment interactions. But those interactions now, it's not the interactions can be standalone. It should be what? There will be some interactions of equipment in hospital 1, in hospital 2, in hospital 3. You guys follow me? So when I say, there are equipment hospital or location interactions, I have to assign them, say that this kind of interactions before it can be standing alone. Now it's assigned to a different hospital. Can anybody give me another example, something similar like this? Anybody try to get into the manufacturing business? Trump said, we're bringing the manufacturing back. But we know that, when the manufacturing coming back, they're going to use a lot of robot. So the job market will be open, but open for the programmer, not open for the low wages laborers, okay? So same things. Say I have some cutting equipment, okay? So I have every flow shop, okay? Or every job shop, I have 3 different machines. And then for every machines, I have different bits, cutting bits, to do the machining, okay? And you guys know what's the difference between machining and 3D printing?
One's taking away material, the other's adding.
Exactly. One is subtraction, the other one is additions. So machining means cut it away. Lathe is machining, okay? And additive is what? It's just print, and put a material on top. It's additions, okay? And what will be the system engineering's job a lot of time? Hot jobs these days. You can get good pay if you know how to do it.
Limiting how much waste.
Getting there. Well, be more specific. If you can say that, they probably will say, we need to hire this guy.
I think they call it nesting, like fitting multiple things into the same sheet.
Exactly. When you print, when you remove material, do you need to have a holding? You cannot say I'm gonna grind this. I need to put it close to the grinder, right? But I have to have a foothold to grab the material so it won't wobble, and I'll have the good calibration, right? But when you try to print something, you also need to have a base. So you grab it, so print it on top or somewhere, right? And a lot of time, it will be a big waste, will be what? If I have a combinations of, I'll do some printing, do some addition, do some subtraction, do some addition, do some subtractions. But if every time I'm doing that, I need to have different footing for different orientation. You guys follow me? Say I'm going to print a pen or something, and then I said, when I do the printing, I can go spiral up this way, or I can go this way, back and forth. But then I need to circle, I need to add something to it. Now, the tricks is that if you're doing printing, you're doing it this printing, you're doing it in this directions, and you're doing the removing or surfacing, you're doing it in this directions. Now you need 2 different. See how I grab the pen in several different way. Then you need different reorientation, recalibration, and you need to find a footing for those things. So what would be nice is what he just said is that, how can I come up with what's that? One stone kill 2 birds, or maybe more than 2 birds, and how to come up with something like that. That's a very important optimization routine. People need to deal with. But no matter additions or subtractions, now you have the printing head, you have the machine. So if you're doing machining, you have not the printing machine, the lathe, the cutting machines, and different head. So same things from experimental design point of view will be what? There will be machine. If I treat it as factor analysis, will be, say I have 5 machines, 5 different heads. So there are machine effects, printing head or cutting head effect, and then I have the machine power, and the heads interaction term, right? So it's supposed to be machine effect M, head effect, a bit effect B, and then machine bit interaction term in the old experimental design, right? But what if I said that, oh, all those printing heads, all those holding device, all those machining heads, they have similar but not identical property. So now, can you assign and say that I have this general interaction term, or you have to say that, oh, here are some variation those interaction terms only happen or belong to a machine, only belong to or A1 machine, A2 machine, A3 machine. So you partition those interaction terms. Remember, before we kind of like just multiply and x times y and then take them out, right? Now you have to say, I have to assign them to one of the machines, okay? So the minute you start doing that, then it's similar but not identical, then that's a nested experiment. But computationally, I'm not going to ask you guys to do Excel anymore, like I promised. Actually, this is supposed to be done before this Thanksgiving. I just show you how to do it in SAS, okay? And if you don't believe me, you can just say, oh, let me go back to my Excel, do the manual computation, and you will check and see the answer exactly the same, okay? And so you guys follow me? If we talk about nested design, what are the key components? If you in a job interview, people say that, we are doing this warehouse, or we're doing this, whatever the process, okay, and we need a system engineer. And can you do this for us, okay? And then they said that, we have different machines or different fitting bit, and then what should we do? Should we consider the interaction terms? And how do you estimate the interaction term? And of course, you can start showing those parallel, not parallel arguments, right? So far, so good. Your job interview is good. But suddenly, they would just say, but you know what? We have all those machines purchased during different era of times. This is bought in the old Bush time. This is during Obama. This is during Trump. Some young machine, some old machine, they're similar but not identical. The minute you heard they're similar but not identical, immediately your head should be start bing, bing, bing. You should mention what term. Oh, then that's not a factorial design. That's a nested design. We need to assign the interaction term somewhere else. Okay? We're good? Oh, okay, so let me find the... Oh, I used the wrong one. Okay, and the material I'm going to use is a very, very classical material. Okay, and let's start from first one. Okay, in the experiment originally, okay, you have machine and machine head interaction term, right? Agree? So the performance could be high, could be low, based on where is the central station mu, and the machine effect, head effect, machine head interaction term. However, if I treat it as a nested experiment, and now suddenly, okay, I have different machine and I have different head. And then, see here, there's no machine head interaction anymore because you will pull the machine head interaction term, add it to, okay? The head effects is the machine effect interaction is within the head. Okay, it could be within the machines. Depends on how you assign it. Okay, and how you decide who should get it. Where is that similar but not identical? You're gonna talk about. Okay, if you said that all the heads are the same, or all the machines are the same, then the whole things will be separated differently. So here, I'm basically said that, watch, I have A, B, C, D, E, okay? And then I'll have A, I'll have head 1, 2, 3, 4. B, I'll have 5, 6, 7, 8. C, I'll have 9, 10, 11. And so every time when I have the head, see the number. If this is an interaction experiment with factorial, should be what? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, right? Do you see 1, 2, 3, 4, 1, 2, 3, 4 anymore? No. Sometimes, okay, different books, they will use different notation. Sometimes they would like to use this, okay? They'll call it HA1, HA2, HA3, HA4, HB1, HB2, HB3, HB4. But no matter how they put it, what do they really mean? They are similar but not identical. So now I have the performance measurement, and then if I want to run a simulation, I will have the effects here, and then I'm gonna. This is the model I will use, but here I'm trying to generate the computation, and the computations are based on the following. First, figure out the machine effect, sum of square, minus overall central, and then you'll get the A effect, the B effect, the C effect, the D effect. Okay? And then you will have the notation here, okay? Head within machine, sum of square. Okay? And when you do that, you will have every one of them. Okay? The machine A, machine B, machine C, machine D, or 1, 2, 3, 4, 5, and add it together. And then you will have your approximation. But see the part I highlight here. Okay? Originally, where is this 46.45 coming from? Should be your interaction term. But now I'm just saying, hey, I don't want interaction anymore. Their interaction will be within the machines, okay? And then, of course, you can calculate the sum of square total, the sum of square machines, and then sum of square error term. And once you do that, people, here's the deal, okay? Machine effect, leave it alone. Head effect, okay, is bigger than before. Why? Because the head effect can be partitioned into this, head in A machine, head in B machine, head in C machine, head in every one of the machines. So this 282 is the sum of all these 5 terms. But these 5 terms really, okay, it's not pure. So in other words, if I want to do it using my old Excel spreadsheet, I just calculate the head effect, calculate the interaction term, and then just lump them together. You will have the head within A, head within B, head within C, and the total sum of square and the error terms will be the same computationally. And what is important here is about the degrees of freedom, okay? And I'll show you the SAS in a second. First, how many machines I have? 5. So 5 minus 1, 4 degrees of freedom. Any problem? No problem, right? Okay, how many heads do I have? You can consider this, right? Well, let me do it in the dumb way. 4 heads per machine, right? If we do it in the old days, should be what? If I consider that it's a factorial design, the head effect should be 4 minus 1, 3 degrees of freedom. Everybody agree? And then the interaction term should be what? 5 machines minus 1 is 4. 4 heads per machine minus 1 is 3. So 3 times 4 is 12. So originally, the Anova table here should be what? 4, 3, 12. Agree? Okay, for those people like to just, like Victoria, want to think it through. You follow me? 5 machine, 4 degrees of freedom. 4 heads minus 1, 3 degrees of freedom. And then the interaction term is 4 times 3, 12. So this 15 degrees of freedom really is in the factorial design is the main effect of head plus the head machine interaction term. But I don't want to partition them that way anymore, because I want to assign this one by one. So machine 1, 4 heads minus 1, 3 degrees of machine A, 4 minus 1. Machine B, 4 minus 1. So 3 times 5. I also have that 15 degrees of freedom. But that 15 degrees of freedom really coming from a different way. Okay? So before I go to SAS, everybody see where this partition coming from now? Is it? Good? Howard disappeared, huh? He was here. Okay. He signed and then he left. Okay. So if we do this, okay, now we can compare the model. Now let me use the code to do that, okay? And the simple SAS code, I think is this one. Okay. Okay. Now, before I go further, first let's look at the data set. Okay. The data set look like this: A, B, C, D, E. 5 machines. So I did it the same way. Okay. Page 192 from Hex, table 7.2, and the data set. I'm doing it in a try to just play a little, more convenience. So I'll have run 1, 2, 3, 4 observation. So I have a do loop 1, observation 1, observation 2, observation 3, observation 4. So look at the first one, 6208, 6208. See that? Next, I'll have the machines. I didn't call them A, B, C, D, E. I call them 1 to 5. So M equal to 1, 2, 3, 4, 5. So now I will have machine 1, machine 2, machine 3, machine 4, machine 5. And finally, the inner loop. Okay? I will have the head is 1, 2, 3, 4. However, here I've put an if statement. This is simple, the grammar here is very similar to your Python grammar. Okay? And I'll tell you, SAS was developed in the 70s first, so use Fortran. So that's the language the grammar looks like. Okay? But now all the SAS code, all the machine code behind it is in C++, I'm pretty sure. Okay, so if machine equal to mm equal to 1 is machine A, machine B, machine C, and then I put an input, the readings, and ampersand, it means what? Read 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 until you read to the end, to the next one, 1, 2, 3, 4, 1, 2, 3, 4. Okay, before I go any further, on this highlighted part, any problem? Simple data statement, right? Yeah?
So just to clarify, that top part of that statement, where you have the do run, to mm, and do head, that's from the original table, correct?
Okay.
Or can you explain why it's 1 to 4 and 1 to 5?
Okay. So, all right. Well, let's see if I make it clear, okay? Actually, let's do it this way. Okay? This is the first run, right? First row is first run, second run, third run, fourth run. So, first row, first run, second row, second run, third row, third. So far, so good? Mm-hmm. Next, okay? Every row, I have 4 belong to A, 4 belong to B, 4 belong to C, 4 belong to D, 4 belong to E, 5 machines, right? So I need to do what? 4 head belong to A, 4 head belong to B, 4 head belong to C, 4 head belong to D, 4 head belong to E for the run 1. So far so good? That's how first loop is the outer loop, row 1, row 2, row 3, row 4 for run. And then inside, okay, I have the machines 4, 4, 4, 4. So I need to do head, head, head. 1, 2, 3, 4, 4 head, machine 1 done. Head, 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 4 head, machine 2 done. So it's kind of like 1, 2, head 1, head 2, head 3, head 4 for A. Head 1, head 2, head 3, head 4 for B. That's how I get that outer loop, medium loop, and inner loop assigned.
Thank you.
Yeah. Be honest with you, stuff like this, I'm just do it because I'm lazy. I'm just whatever they give me, I just follow that. If you ask me, if there's any rule on, which one's outer loop, which one's inner loop, depends on habit. Okay. A lot of time, I would rather talk when I work at an insurance company. I would rather talk to the engineer. Whatever they feel they can visualize, I'll use the sequence they come up with. Let me elaborate what I'm talking about here. Be a little careful here. Okay. So let me give you okay, people. Can I have This is my block 1, block 2, block 3, block 4, okay? What I'm saying is that, is it possible that people will say that, hey, the mental picture we have is machine 1, 2, 3, 4, head 1, 2, 3, 4. Within the 1, 2, 3, 4, 4 run, 4 run, 4 run. We want to read it that way. Can we set it up that way? Yeah, there's no such things as in the reading sequence to say that, oh, which one. I think what you're trying to ask me is that, is there a rule in SAS, which one should be the outer loop, medium loop, inner loop? No. Whatever people can see it, it's there. But I do know this, as I always do, okay? Whatever rule I come up with, okay, I better do a proc print. You know why I do a proc print? Just double check. Make sure that, hey, this is a run 1. I have a machine A, and then the reading is 6. And then I have a run 1. Head is 2. Machine A is 13. And then you go back and say 6, A1, 13, A2, A3. Double check. Yeah. And you know how to double check with a huge loop? Check the first one, check the medium one, check the tail one. If front is right, middle is right, tail is right, probably the whole thing's okay. Okay? Next. Okay, we read it. Okay. Let's skip the GOM, various composition for a second. We just talk about the GOM here. Okay, now, people, if, okay, let me just create one for fun. If this is treated as a factorial design, okay, you have machine head model should equal to what? Not head within machine. You should have is what? Head machine times head, right? Machine effect, head effect, machine head interactions. Agree? And of course, you can write it as a shorthand, like what? Model reading equal to machine pipe head, right? If you do a machine pipe head, that means the statement I block is exactly the same statement up here, okay? And then next things here is we said that we're going to test the machine effect and the error term here, okay? The error term here, this time, we're saying that we'll use head within machines. And that is basically, we're trying to show the statement of the computations here, okay? And I'm not gonna do that immediately. I just wanna run, okay, let me just kill this part first, okay? And here we just say that, okay, I would like to run the multiple comparison using the SNK or student, the subway station for multiple comparison. And then we'll create output, residual plot, and prediction, yada, yada. Okay? I can even, if I don't do residual analysis, I can block this. Everybody agree with me? If this is factorial design, we just write proc GOM data from what we read, class, machine, head, and machine head interactions, and do multiple comparison for machine, or maybe do multiple comparison for head too. Okay, if you want to do both. But let's just say do this. Okay, this. Would you agree with me? This is what we have in the old days. Yeah, and you can do it in Excel. You can do it the central station, the subway station way, right? So far so good. So we can run it, and if you run it, you would do a multiple comparison, everything's okay. But the things I would like to show you here is people watch model. Use up 327 sum of square can be partitioned into main effect of machine, 4 degrees of freedom, head effect, 3 degrees of freedom, 46, and then machine head interaction, 236. Those are friendly terms, right? You've seen it before, right? Just do me a favor. Add the head effect and the machine effect together. What will you get? 282.87, right? Right? If I add the head and machine together and use up 15 degrees of freedom, right? And what is that? 15 degrees of freedom, 282. See that? That's why I don't want you to think about the computation directly, because if you think about the computation directly, okay, you feel like, oh, this nested design is something totally new. You can think about it like a factorial design, but in reality we say no, because it's similar but not identical. So we cannot treat it as a factorial design. So we need to pull them back in, okay? And the next thing is, if you check the total degrees of freedom and total sum of square, everything's good, right? But we know that if you put this SAS as your analysis for your boss, you asking to be fired, get a pink slip before the Christmas, because it's wrong. The true analysis should be this one. So let's block this. Okay, and this is the experimental design we should have. Okay, now reading machines, and every head is within the machines. We have different heads to be used. Okay, and then when we test the machines, okay, we will say that why the head into machine with different machines need to be checked, because originally error term is error term by itself. Now we have to say that, hey, if I'm using machine A, then the variations will be because of different head I used. Machine B, I'll have different machine heads I used. So in other words, is that this effect, okay, the machine is true fixed effect. Well, let me give you another example. This one is here. How many of you like to watch Olympic figure skating or gymnastics? Okay, yeah, triple loop, whatever. Okay, and so a lot of time, let's just say that we have the top figure skater, usually Germany, the Russians, the Chinese, the U.S., Canadian compete, right? So let's just say that there's a set of ranking, A, B, C, D, E of those people. Good, bad, good, bad. Agree? Now, do you think it's possible, because of different judges giving the score, sometimes we could bias a little bit, the world champion become number 2, and so on, right? So first thing first, what do you do? Usually what we do. What's the treatment people use? And this is actually the same thing people use in eBay. Bidding for some products. A lot of time we use the same tricks. What's the tricks we used? Anybody? Abandon the highest one and the lowest one. Because if someone said, oh, that's my guy, I'm going to give a lot of good score, a lot of good grade, then, say your take-home exam, I give it to 5 TA to grade, okay? If, your performance good is good, bad is bad, should be what? Regardless who's grading it, good is good, bad is bad, right? But sometimes it could vary a little bit. So we can consider this is the uncertainty introduced because of the judges we have, the referee we had. Or, in eBay, do you think eBay there are people intentionally or even, on other bid? It's like this. I really don't want this piece of furniture or something. But you know why I'm bidding it? I'm just want to ruin other people's opportunity, right? So they also try to get rid of the highest bid and lower bid. But generally speaking, if I have A, B, C, D, 5 machine here, or A, B, C, D, E, 5 competition, 5 candidate, 5 whatever here, generally speaking, the highest one should be the high, the medium one should be the medium, the low one should be the low one, right? But I need to consider that when I compare this, there are the randomness introduced because I'm using different head. And remember why this is so critical, because am I using the same 4 heads and said, oh, I'm going to use this 4 heads for machine A, and then I'm going to remove those 4 heads and put it in machine B, in machine C, in machine D. If I'm using exactly the same head, machine by machine, then that's what? A factorial design again. But remember what I said, this is a nested experiment, so in other words, the heads we used are what? Similar, but not identical. So when you test this, you need to say that, oh, the error term I'm going to use is, I need to use the error terms had by different machines. Okay, and then of course after that you can run your old days, the Durbin-Watson test, independency, the equal variance, all that stuff. Okay, so now let me just show you how this is run. Okay, so this is your QQ plot, all that stuff, equal variance. I'm not going to waste my time there. The things I would like to show you, something. I can recognize. Okay. Clear all. Let me see, where did I do wrong? Anybody can tell me where I did wrong? Why I didn't get any output? You need to run, right? You don't put run, they're not going to run. Oh, and here are a couple plots that you can do. The normal plot, QQ plot, but the data I said that, plot a residual or the predictions. I create an output file called OOO, And if you don't like to call 000, you want to put 40, that's fine. Those just, remember, I said you have to have appendix for all the legal document. That's your univariate. But the key things we need is this piece. Let me do it one more time so I can show you. Here we go. Okay. So now you can tell. First thing first. How do you know? Just by looking at SAS, you know this is a nested experiment. Symbol is head within machines for one. The other thing is what? Do you have interaction term? No interaction term. So you know that that's it. And if you compare this 45, 282, that's exactly the same things for T5, 282. Okay? Okay, next, okay, here I'm trying to plot machine by machine, okay, the whisker plot, okay, and you look at the whisker plot, okay, one thing's immediately you will notice is which one got a lot of variation. B? B got a lot of variation, okay? And then this thing is important that when I introduce Taguchi design, a lot of time we look at this, is that Taguchi is robust design. Robust means what? We're insensitive to the perturbation. And what is disrupting the machine's performance? Different heads, right? So here, if I said that, hey, the Russians figure skater, they are very, very robust. What does that mean? No matter who is the judge, who are the referees, the performance is consistent, doesn't vary much. Then you should see them shrink. Okay? So you first thing you want to see is low variations, small variation. And the second thing you would like to see is what? The average performance as tall as possible. And of course, at the end, okay, it's not in nested design. In Taguchi, I'm going to talk about this. I want the performance good, but I want a performance consistently good with little variation. Okay? If I want a response surface to be max, always max, to be mean, always mean. Next. Okay? You can have your comparison here. So SNK tests say that A is better than A is higher than D, D is higher than C, C is higher than B, B is higher than E. However, look at a grouping. Can I separate them? They're all in AAAA, means that I cannot separate them. They're all bundled together. So I cannot tell the differences between from machine to machines. In other words, is that even though there are some things here, but the statistical power is not good enough to separate them. Okay? So you can do a multiple comparison, but there's no significant multiple comparison. So far, so good? Okay? Next, now we're going to try to run this, the final touch. Okay, this time, watch, okay? I take the data, I will store the data. Young lady, here is the part that if you read it in one way, but then you say that, hey, I don't want to read it that way. You can say that, hey, bring me the data, but do a proc sort. Sort the data by machine. So now it become what? All the machine one, it will look like this. reorder machine 1, then machine 2, and machine 3. So you can reorganize them that way. Okay? And if you reorganize them that way, and then you can do another comparison. Okay? And this time, you can run a SNK test. Okay? And for machines. So this is pretty much the same things. However, okay, I want anybody can answer this question for me. What have I done here? Data. Set means copy. I copy the original data. And then I copy the original data. I said, if run equal to 1 or run equal to 3, get rid of it. So in other words, is that the first row and the third row, I delete them. So I only use 2 run of the data set to do the nested design. What am I doing here? Same things I've been talking about a whole semester. When you run experiment, if I can use half of the observation and reach the same conclusions, I should do it that way, right? You should always impress your boss in saying that, originally the plan is taking, a year, $500,000 to get what we get. Now I can use 6 months, $200,000, I can reach the same conclusions. So here I'm just doing it for fun and said, rerun this data set and then using half of the data. So let me run it and then do a comparison. Okay? Okay. First of all, before the comparison was, we're using all 4. The sequence is what? The sequence is, I cannot find it. Give me a sec, okay? Yeah, the original sequence using 4 run, right? 4 run, 4 head, 16, 16, 16. The sequence A, D, C, B, E. Okay? Even though it's not significant. Okay? After I'm using not yet. After I'm only using A observations, right? I killed half of the run. The sequence still A, B, D, C, E. And before I cannot tell the differences, less observation, definitely I'm not going to tell the differences. Okay? And then this is the case. There are situations the opposite, okay? Sometimes when you have competition, how many of you seen the movie Ford versus Ferrari? When the CEO, the Ford second, tried to compete, he wants to win, right? And for a while, he want to, impress his ancestor, right? His dad. So what did he do? Putting more money. So in other words, is that if he's running the experiment, rather than cut down the number of experiments, what would he do? He add more run, because he only try to do what? To show that the 4, even though, I'm only win Ferrari just by a tiny bit, but I can significantly showing the differences. And that will be the situation. Rather than cut down the number of run, you increase the number of runs. Okay? Second, now I'm going to talk about machine by machine. Okay? You can have a comparison here. See here? I'm doing this SOAR, okay, by machine. And then when I run this experiment, people highlight this part. I have a statement here called by machine. You see that? Proc GOM, class, machine head, model, by machine. You know what we're doing here? We actually are doing this. It's almost like we're treating the experiment. Ignore everything, okay? People, can I only look at within A? I have 4 head, right? Can I consider that within A, I have 4 treatment, head 1, head 2, head 3, head 4, single treatment experiment? Can I do that? Can I? Yeah. So this is 16 is your what? Homework 1, right? For machine A. And then can I have 5, 6, 7A? 16 observation is my machine B single treatment experiment, right? So if you do them one by one, within A, within B, within C, then you can come up with this within A, within B, within C, sum of square. So the within A sum of square, within B sum of square, within C sum of square here. Those A, B, C, D, E sum of square. Okay? How can I get that? Overall, you can consider that 282 is from where? From the machine head interactions plus the head effect, right? But if you want to do it differently, you can consider that, okay, within A, I have a 16 observation, 4 head. So I can have a sum of square there, sum of square there. So when you break them down into machine A, 16, 4 treatment. Machine B, 4 treatment. Machine C, 4 treatment. Now, when you add those 5 experiments, within A experiment, within B experiment, within C experiment, when you combine them together, you get exactly 282. You guys follow me now? Yeah. So, nested experiment, if you look at it this way, okay, what's the benefit? Or do you think that it's a what I'm trying to say is that who should I ask? Kevin, factorial design experiment. Okay, what's the purpose of running factorial design experiment?
Make sure that when you run, you want to be able to run.
To find what?
To find effect with the list different operations.
To find what?
To find the effect in the variable.
Factorial design, what can we find that we cannot find in the single treatment or in the blocking experiment? Factorial design, what we're looking for.
We're looking at different effects that you find
No. Yeah, I know you try to say parallel, not parallel. So what parallel, not parallel, that reflects? In interactions. Yeah. And so here we just said that no more interaction. You can consider that it's almost like have a machine and then 5, each machine's a single experiment. So, for example, if say we want to compare, 5 schools, okay, around this neighborhood, NC State, Clemson, UNCC, NCA&T, let's add one more. So every school we're teaching with the system engineering, we're teaching certain things using certain material. I can just say that, hey, let me just run within our campus what's going on. within another campus what's going on. So now all I have to do is just lump them together. That is the total campus effect. But then on top of that, we're using very similar, because we are under ABES evaluation, so we have a curriculum effect. Curriculum effect, campus effect, but campus effect is within campus, right? So now this is a run, so you have 50, 16, and then if you look at the SAS, okay, you will see, oh, this is machine E. Let me start from machine A. It's machine C. Here we go. Machine A. 50 is the 3 degrees of freedom, the error term, and then the total sum of square, and then how I check my things. Okay, 50, and then how I check my error term, 64 divided by this. So this whole thing is done this way. Okay, before I go any further, okay, I want you guys look at this table. I want you to look at this table, and then I want you to look at the SAS code here. And let me make it smaller. Okay, look at the table. Just by looking at the this Anova table, can you visualize how the data is arranged for nested experiment? Look at the GOM, okay? Can you see the GOM? Understand how we come up with the overall ANOVA. And then we come up with this one by one ANOVA by using this proc GOM by machines. Means every machine is 16 treatments. Okay, I'll give you 2 minutes, 1 minute here. Make sure you can visualize it. You have the material. I'll give it to you. Okay, this is not, like I said, the torture is at the beginning. Now we just let a SAS run as you see how quick I can get it done. But can you abuse SAS? And just compare the two, okay? Make sure you can do it. Okay, just wiggle your finger. You're good. Then I'm going to move to the next one. Everybody good? Okay. Now? Oh, huh? 5 minutes again? Oh, yeah. Okay. So here are all the other stuff I'm not going to get into. Okay, let me have another, here's the machine interactions experiment. I have a gun loading problem, okay? And I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I have 9 teams. Every team, they will use, method 1 and method 2 to load a gun. Okay, this could be a big cannon. Okay, these days people are actually talking about a lot of intelligent gun design, and the intelligence is that when the material, it's intelligent to identify the target. So really, it's not an old cannon just shoot and forget. These things actually can be guided, can be laser guided or GPS guided, can shoot for long range. But then, so gun is coming back, okay? And for method 1 and 2, so totally 2 observation, 2 observation, 2 observation, 2 observations. So what we really want to know is, okay, there are first group 3 teams, second group 3 teams, the third group 3 teams. Every group got 3 teams, and then 2 methods. So if this is a factorial design, it should be what? There are team effect, there are method effect, there are the group effect, and then there are the team method interactions. For example, let's just say that some team people are from Scandinavian countries, extremely tall. They're Dutch. And then some team, they're from Southeast Asia. They are very short and very agile. So different anthropometric profile probably prefer different loading method. And so I can run this using factorial design, right? But now, again, what we're really trying to do is try to run this. Oops. You know what? I'll do it next time. And but everybody got a pretty good idea that how to see nested design, right? Yeah. Memorize those keywords, okay? Because that help you visualize the whole thing. Okay. See you.